Alright, this video is going to be on the Net Change Theorem. And the Net Change Theorem says that the integral of a rate is the net change. So the integral of a rate is, I don't know why I wrote on, is the net change. So if you remember how we would get the rate in the first place, that was the derivative. Derivative is an instantaneous rate of change. So if you integrate that, you're going backwards. You're finding the antiderivative, or you're finding the original function. So the original function is what's going to give you the net change. And there are some things that we know about net change, or that we, how we might express net change. So that might be something like the total change. That might be worded as accumulation. It could be worded as the total amount. That's definitely wording that you've seen before. It might also be labeled as displacement. So all of those things are just different ways of saying the net change of something. Right. So here's the notation that we're going to use. We're going to say the net change. And so R is saying the antiderivative. So this is lowercase r. This is a function. This is its antiderivative. Or we could say that this might be the derivative of something, and this is the original version. So it would be the antiderivative evaluated at B, subtract the antiderivative evaluated at A. So basically, we're just taking this integral and we're evaluating it for the two values. All right. So here are the examples, and these are word problems, so I apologize in advance if you get a cramp in your hand at so much writing. So we're going to say at 7 a.m. water begins leaking from a tank at a rate of 2 plus 0.25 T gallons per hour, where T is the number of hours after 7 a.m. So at 7 a.m. water begins leaking from a tank at a rate of 2 plus 0.25 T gallons per hour, where T is the number of hours after 7 a.m. How much water is lost between 9 a.m. and 11 a.m. So if you read this problem, you can see that they gave you a rate, and that means that the net change theorem applies. And so we're looking at the integral of the rate is the net change, and we're trying to find the total change, or the accumulation of water that leaked out between 9 and 11 a.m. So we're going to say that we are finding the integral of 2 plus 0.25 T dt, and T equals 0 would be 7 a.m. So 9 a.m. would be 2, and 11 a.m. would be 4. So we are going to find the antiderivative of this, and then we're going to evaluate it from 2 to 4. So this would be 2T plus 0.25, this is 1/4. So 1/4 divided by 2 would be 1/8 T squared. So first I'm going to say 2, I'm going to plug the 4 in. minus what I get when I plug the 2 in. And that gives me 5.5 gallons if you plug it in. So the math that we're doing here is not necessarily new. We just have to recognize when the situation is appropriate for us to use it. So we're going to write our answer in a sentence because that's what we do with story problems. I know you guys love it. So the amount of water lost between 9 a.m. and 11 a.m. is 5.5 gallons. Okay, example 2. So this one says the marginal cost of producing X computer chips in units of 1,000 So the units of chips is per 1,000, and the amount of the cost is in dollars per 1,000 chips. And if it's per 1,000 chips, it's really per each unit of the chips. So just think of it that way. So dollars per 1,000 chips is C prime of X equals, and I'm actually going to write this on the next line. C prime of X equals 150X squared minus 3,000X plus 17,500. So the first thing that we're going to do, that was a situation. The first thing they're asking us to do is find the cost of increasing production from 10,000 chips to 15,000 chips. All right, so this cost that they gave us is a rate of change because the cost is changing depending on how many chips you're making. So the more chips you make, the more efficient your procedures can be for that sort of thing. Kind of if you think about like how it works with making food, it's cheaper to feed a lot of people than it is to just feed one person because you can kind of break it down across those people. So anytime you are making more things, then the cost is going to be cheaper for each thing. So that's what they're saying, is that this cost equation is a rate of change. And so they're asking us to change, find the increasing production from 10,000 to 15,000 chips. So we know that we're going to be finding an integral from 10 units to 15 units because each unit was in the thousands. And it's going to be C prime of, this is an X, not a T, dx. And I'm going to go ahead and show you guys how to do this in your calculator. So if you go ahead and hit the math button and then scroll all the way down to where it says int for integrate, so fn int, number 9. Then we're going to say we're going from 10 to 15. And then in here, we're not going to write C prime of X because our calculator doesn't know what that is. We're actually going to type in that equation. So 150X squared minus 3,000X plus 17,500. And then we have to put dx in here. So we're writing down, we're using the same variable that the problem is using. And then it tells us the answer, and we didn't even have to do the work for it. Isn't that nice? So sometimes I'll let you use your calculator to solve these. Sometimes I will require that you do it by hand. Okay? All right, I'm going to go ahead and write that sentence. So it costs $18,750 to increase production from 10,000 to 15,000 chips. Okay, part B for the same. Determine the total cost of producing 10,000 chips when C evaluated, so this is the original function, not the derivative. The original function evaluated at 1 equals 35,000. All right, so we have a few different ways we can do this problem. One way would just be to take the original problem and find the antiderivative and plug 10 in. But I'm going to show you guys kind of a tricky way to do it that's actually going to make your life easier if you understand the process that we're using. So I'm going to say if I was to integrate this from 1 to 10, so I'm saying 1,000 to 10,000. That's going to be if I evaluated the original function at 10 and if I evaluated the original function at 1, right? Now, if I evaluated at 1, this is that 35,000 that I get. Evaluating it at 10 is the answer that I want to know. I want to know how much it costs to produce 10,000 chips exactly. So not the changing rate, but what it exactly costs. And so what I can do is I can plug this part into my calculator. So this is an answer that I already knew. This is what my calculator just found. So I can go ahead and add the 35,000 over. And then I know that the cost of producing exactly 10,000 is $93,950. Okay, one last example. We're going to say the velocity of a particle, and velocity is rate of change, right? It's how the particle is moving. So the velocity of a particle is t to the third minus 10t squared plus 24t feet per second. So I wrote part A, but I did not have a part B anywhere. So we are going to find the displacement over 0 to 4, 4 to 6, and 0 to 6. And then we're going to explain what these values represent. All right, so if you guys recall, when we were doing these velocity problems, what we typically did if we wanted to find displacement is we would plug 0 into the original function, the s of t. We would plug 4 into the s of t, and we would say the end minus the beginning, right? So s of 4 minus s of 0 is what would equal the answer. So for us, that's the exact same thing as what we're talking about with this net change theorem. So now we're saying evaluate the integral. Actually, I'm going to go ahead and shorthand this. Evaluate the integral from 0 to 4. And we know that if we were actually to go back and do the math, we would take v of t and we'd go back, we'd figure out what s of t was, and we'd evaluate s of t at 4 and s of t at 0. And we'd subtract those two things. That would tell us the displacement. But we're actually going to go ahead and just do those on our calculator so we can save ourselves some time. So we have 0 to 4, 4 to 6, and 0 to 6. So I'm going to hit the math button and go down. So this is math that we have done before. We have just done it by hand before, and now we're using our calculators to do it for us. So if you want to do it in terms of x's, you can. If you want to do t's, you can. So t to the third minus 10 t squared plus 24 t d t. So that's 42.667. And then we'll do the same thing from 4 to 6. Negative 6.667. And then we'll do the same thing from 0 to 6. 36 exactly. All right, so if we look at this, you can see that the displacement, so the starting position versus the end position, so not talking about if it went back and forth at all, but just the start versus the end, is these three numbers. So I'm going to say the displacement of the particle from 0 to 4 seconds was 42.667 feet. From 4 to 6 seconds was negative 6.667 feet. So that means it was moving in the negative direction. So if it was going up and down, that would be down. If it was going left and right, that would be left. And then from 0 to 6 seconds was 36 feet. All right, now we're going to do one more thing because I've just figured out what my part A and my part B was. So part A, this is part A of the problem up here. Part B, we're going to find the total distance. So if we don't want to just know the beginning point and the end point, if we want to know all the distance it went, where it was going backwards and forwards, and add up those distances, regardless of which direction they are, then we can evaluate the same integral. So we're just going to say from the beginning time to the end time from 0 to 6. But we're going to put the velocity function in absolute value. So that means that even if that answer is negative, we're going to count it as a positive, and that will allow us to add up all of our different distances together. So unfortunately I have to retype this whole thing. I've tried putting it back in before with the absolute value signs just around it, and I was not able to do it. So if you can figure it out, that'd be awesome, because it would save you some trouble for sure. But there's my absolute value sign. I'm going to go ahead and type the equation in again. So we've got t to the third minus 10 t to the second, and then plus 24 t dt. It's taking longer for the calculations this time. So the total distance that it traveled over those 6 seconds was 49.333 feet. And if you have space on your notes, you can go ahead and write that in a sentence.